Welcome to our last part of Chapter 3, Unit A. We're going to be talking about temperature this time. So typically we refer to temperature on a relative scale, degrees Celsius or degrees Fahrenheit. Unfortunately, this causes a lot of problems in doing thermodynamic calculations. So we usually use an absolute temperature scale. Now this will be derived for you in the thermodynamics course, but for now, just what this scale is it's a scale that cannot go to negatives. So the minimum value is 0 and it's a fixed value, fixed temperature. So for the SI units, we use the Kelvin scale, which is the temperature in degrees C plus 273.15. For American engineering units, we use the Fahrenheit scale plus 459.67 to get to degrees Rankine. Frequently, we're only going to be dealing with temperature differences. And if you're only dealing with a difference, well, okay. If I have two temperatures that are both in kelvins, and I want to know the temperature difference, remember I can only subtract things that have the same units. Well, those kelvins are both temperature in degrees C plus 273.15, and those are going to subtract off, leaving me with the delta T in Kelvin is exactly the same as delta T in degrees C. And you can do the same thing for degrees Fahrenheit and degrees Rankine. So that makes it a little faster to calculate things, and it's going to really, in some future classes, really make things easier for you if you'll just remember this and avoid all these tedious conversions. So if we look at an example problem, so 1 week this summer, temperatures varied during that 1 week from 68 degrees Fahrenheit to a high of 103 degrees Fahrenheit. So what are these temperatures in degrees Celsius? What are they in degrees Rankine? And what's that temperature difference, the delta T, in degrees Fahrenheit, degrees Celsius, and degrees Rankine? This isn't terribly difficult. Degrees Fahrenheit, 68 degrees Fahrenheit is also 528 degrees Rankine. We just add. And to convert to degrees C, you just use the conversion formula. Okay, 103 is equivalent to 40 degrees C, roughly. That delta T, if I subtract these, is 35 degrees Fahrenheit. If I subtract these, it's 35 degrees Rankine. But remember, these are the same, right? And the temperature difference in degrees C is 19.4 degrees C. It would also be 19.4 Kelvin. So, now here's one that's a little trickier. Now those unit conversion formulas that are in the book, they're kind of hard to use when you're using temperatures that are built into a formula. This is going to come up a lot in the heat transfer or transport courses that you'll be taking in the future. So the overall heat transfer coefficient is a way of evaluating how heaters or coolers work. So in this particular case, we have an overall heat transfer coefficient of 85 watts per meter square Kelvin. And the temperature used here is a delta T. Now that's important for us to know because if I'm doing a unit conversion, delta T in degrees Kelvin is the same as in degrees C, right? And delta T in degrees Rankine is the same as degrees Fahrenheit. So the question is, what is this coefficient if I were to switch it over to American engineering units? So those would be BTUs per hour. Watt is a joule per second. Feet squared instead of meter squared, and degrees R instead of kelvins. And so if you play the little unit game, okay, watts to BTUs, so BTU per is a watt hour, 1,000 watt hours. There are many versions of this that are variations here. Meters to feet, square that. And then a Kelvin is 1.8 degrees R, or a degree C is a 1.8 degrees Fahrenheit. And so this 85 watts per meter square Kelvin is 15 BTUs per hour foot square degrees R. Alright, so this concludes Unit A. So we've covered chapters 2 and 3. Don't forget that there is an online exam in Canvas over this material.